In this clip, we'll explain how we can differentiate composite functions. And this is a very important rule to learn because you will use it over and over and over in this course. First, let's have a look at the definition of a composite function. So a composite function, f composed with g, that's how you read this little circle symbol, so f composed with g, uses the output of a function g as the input for a function f, right? So what this means is that we have some domain. Here on the left, we have this domain, and there's a point in this domain, let's call it x, and we're going to use this value x as the input for the function g. So we compute g of x, and we end up in this range. Now this range is going to act as a domain for the function f. And so we use g of x as the input for f. So we obtain f of g of x. So first we apply g to x, and then we apply f to that result. And so we obtain f of g of x. Now you can also think of this immediately, right? Going from the domain of x to the range where we have f of g of x. And so then we have a composed function, f composed with g. And you can also think of this as first we apply g and then we apply f. So we go from right to left. First we apply g to x and then we apply f to g of x. Okay, so in order to differentiate this type of functions, we will introduce the chain rule. Now the chain rule states that the derivative of the composite function f of g of x at x is equal to the derivative of f at g of x times the derivative of g at x, right? So there's some kind of product going on. Let's look at a very simple example. So let's look at the function y is equal to 3 over 2 times x. It's a very simple function, and we're going to do something artificial, right? A small exercise. We can think of this function as a composition of two functions, and the first function is y is equal to 1 over 2 times u, right? That's the first function. And then u is equal to 3 times x. So now we have two functions, 1 over 2 times u and 3 times x, right? And I can plug in 3 times x in this one, and then I obtain the original function. But you can think of this as two functions that are composed. And now we can have a look at the derivative. So if you look at the derivative of y with respect to the variable x, well, that's obviously 3 over 2. It's a very simple linear function, so the derivative is 3 over 2. But the derivative of y with respect to u for this function here is 1 over 2. And the derivative of u with respect to x is 3. These are all simple differentiations. And now we notice that, well, the derivative of y with respect to x is equal to the product of these two derivatives, right? 1 over 2 times 3 is equal to 3 over 2. So the overall derivative, y with respect to x, seems to be equal to the product of these two derivatives, of y with respect to u and u with respect to x. Now this makes sense intuitively, because if y is equal to f of u changes half as fast as u, and u is equal to g of x changes 3 times as fast as x, then you expect that y changes 3 over 2 times, the product, as fast with respect to x, right? So that's the idea of the chain rule, right? Step by step in the chain, you take the derivatives. So this is another way to look at it that is reminiscent of this definition of a composite function, right? So we have our domain x, and we go from x to g of x, and then we go from g of x to f of g of x, right? That's the illustration of the composite function that I explained earlier. But now you see that the rate of change at x is g prime x, right, for this function g. And the rate of change at g of x, at this new point, g of x, is f prime at g of x. And so the overall rate of change of this function f of g of x is then the product of these two things. So f prime g of x times g prime x. That's the idea of the chain rule. Now let's look at a simple procedure so that you know how to apply this. The procedure goes as follows. You always differentiate this function, this composite function, from the outside to the inside. Right? So let's have a look at a very simple example. So let's say we want to differentiate f of x, and f of x is equal to x squared plus 1, this is a function, to the power 2. Right? And so you can think of such a function as a composite function, because you can think of f of x as f of x is equal to g of x squared, where g of x is this interior function x squared plus 1. And so the outside function is the squared function, right? We take something to the power 2. That's the outside function. And the inside function is g of x. And what you do then is you differentiate from the outside towards the inside. So first I differentiate the outside function. The outside function is a square function, right? So something to the power 2. So that means that that's 2 times something. And then I differentiate the inside function, and that's in this case g prime. And then you multiply those two different derivatives to obtain the overall derivative of the composite function. So f prime is equal to the derivative of the outside function, 2 times g of x, times the derivative of the inside function, g prime of x. And if you then plug in the definition for g of x, then you get 2 times x squared plus 1, and this derivative is 2 times x. And so this is your overall derivative of f. All right? Now you can try. So try to differentiate this complicated looking function. So you take the logarithm of the sine of x to the power 3, and I gave you a tip with coloring these functions in different colors. So you see that in this case there will be 3 functions. There is an outside, an interior, and another interior function. And so you will have to do 3 derivatives. All right, good luck.